amount of current that a capacitor allows to flow is dependent on the capacitance and frequency. So a larger capacitor, will allow more electrons to flow, obviously. We'll just say more current flow. And a higher frequency will, having trouble here, allow more current to flow. You guys know the sign of the strokes, I hope, and you'll help me out when that happens. All right, so a larger capacitor allows more current to flow. Why? Because there's more plate area, and it allows all the electrons to fill up the plates before they get full. So if there's lots of room, you have lots of plates going, you have lots of current flow. And a higher frequency, because if we turn it around, think, well, a slower frequency, while it's still building up, maybe the capacitor is already full, and so current would stop flowing altogether. If we had a little light, it would start dimming down. And then the voltage would come up and start reversing the other way, and then it would start to brighten up and then dim down. So if we're changing frequency back and forth, then the plates don't have time to fill up, and so there we go. Capacitance in a circuit. No, total. We'll say total capacitance. Total capacitance. It's one like way out to the outside there. Total, maybe CAPACIT and CE in a circuit. It is, well, let's do this. We always do series first, right? Yeah. So we got this, then another one, then another one. And so if we had to add this all up, it would be current capacitance total equals the capacitor of 1 over 1 plus 1 over C2 plus 1 over C3 over 1. What? Huh? No, what is that?
It's like resistance.
It's resistance, but it's the opposite. Now, why would they? Okay, and if we look at parallel, it's going to be C total equals C1 plus C2 plus C3. The heck you say? Why is that? Well, let's just look at parallel real quick and think about it. Well, we have electrons flowing this way and this way and this way. And what do they see? They see one large plate and another large plate. So you just add up the area because it just sees, you just add up the area of the plate. But what's going on up here in series? Well, we have electrons moving this way, which will attract to this, and then repel some of their electrons this way, which will fill up some of this and repel some of those and go this way. You can see we're just kind of diminishing down here. And we start losing the power as we go because you're dependent on this long string. So it looks more like those parallel. You just don't have as much capacitance going on. So if you stack them up in series, it's like resistors in parallel. So it is the opposite. I have to move over here. It is, where was I here? Go to black. The opposite. It is the opposite of resistors and inductors. I'm not going to write all this. The reasoning is that when capacitors are in series, the total capacitance is less because the center two plates do not really contribute to capacitance. In a parallel, the total plate area is added together because each capacitor acts independently. Total capacitance is the amount of capacitance. Oh yeah, I like this one. It's just a point. Total capacitance is the amount of capacitance, but that does not tell us, the actual opposition to current flow. Tell us the actual opposition to current flow. So there's, I don't love that sentence because it talks about this opposition to current flow, which to me is almost backwards of what we've been talking about. We're talking about how capacitors really make current flow. There's no opposition. So I could almost cross this out if I wanted to, but it does not tell us the actual, like if I wanted to do that, does not tell us the actual resistance. Because it's going to act like a resistance, these capacitors, when we start playing with them, just like an inductor does. And the reason why, because you think about the inductor has counter EMF, well, there's no counter EMF here, but as they fill up, there's going to be this opposition to current flow. You can't have current flow once it's full, so you can go with that. But it is, in a sense, the opposite of an inductor. And we call it, what do we call the other thing with inductors?
Inductive reactance.
Inductive reactance. Now we're going to talk about capacitive reactance, which is the opposition to, well, I'll stick with my notes, of current flow in a circuit, of current flow in a circuit. Capacitive reactance, the opposition to current flow in a circuit. What was inductive reactance? No, what was inductive reactance? What was the definition?
Inductive reactance is the effect of inductance in a circuit.
It's what?
The effect of inductance in a circuit.
Okay. Maybe we should have called it the opposition to current flow in a circuit. All right. So about this capacitive reactance, it is measured in ohms. But due to phase shift, I feel like I already wrote this, is not considered, you can just cut and paste on your piece of paper, resistance. It is represented as X of C. It is inversely proportional to capacitance and frequency. In other words, reactance will decrease So in other words, will decrease if capacitance or frequency increases. So reactance will decrease if capacitance or frequency decrease. So what was that formula for the inductive inductors?
2 pi times frequency times
2 times pi times the frequency times the L, but this time we're going to go with C. So 2 pi FC. Does that look familiar? Okay, but it is the inverse. So 2 pi FC, 1 over that. And it's going to be represented in ohms. Obviously, F is the frequency, and C is the capacitance in farads. So F equals frequency, and C equals capacitance in farads. Woo! Got through that. That's all I got to say about capacitors.
I'm just curious.
What I'm going to do now is switch gears a little bit. We're going to put it all together.
Oh boy.
And I think in a lot of ways it starts to make more sense at this point. But we've taken each piece on its own. We've talked about resistors. Nothing new there, right? Talked about inductors. A lot of new stuff there. X of L, right? Inductive reactance. And we know some things about what makes it more or less inductive reactant. But the key thing was the more henries we have, the more inductive reactance we have, right? So the more coils we start adding, the more henries we start adding, the more Eli is going to take effect, which means that the current is going to E comes first, then L, then I. So voltage will lead the current. So that means that the current follows, lags behind.
90 degrees.
Thank you. And then if purely. So yes. Then we talked about capacitors, which have a tendency to let the electrons run off like Disneyland. And so that means that the current is going to lead. The current goes first. It's going to lead. Thought we had it. We'll just remember Eli the Iceman. Okay, so we'll write that down. Eli the Iceman. So in a purely inductive circuit, Eli, in an inductive circuit, the voltage will lead because it comes first, and the current will follow. And then in a capacitive circuit, which means it has more capacity than it does inductance. Thank you. Well, that's not easy to do. So we have a circuit that has coils and capacitors. And then you're going to look at it and say, well, if it has an equal amount of both of them, then we will have the current and voltage in phase. So nobody leads anybody. It's perfect. Right? They're both following each other. Just nice. That's what we want. That's the best circuit right there. It's the most efficient. But if we have it perfectly going, and then Zach over here decides that he's going to plug his a fan to keep himself cool for whatever reason. So his fan's got a motor. That's an inductor. So now what's going to happen? Now it becomes an inductive circuit because it has more coil than capacitor. So he's screwed up the circuit, and now the voltage will lead and the current will follow, and we start to get out of phase. But I don't like that, so I pick up a capacitor and I throw it at him, and that sticks to the circuit. And so now I've got both of them. So now I've got more capacitance, so now it becomes a capacitive circuit, which means that the current will start to lead and the voltage will start to lag. Okay? Got it? So we take all of these and put them together. In a DC circuit, we had a resistor and a light and something else and something else. And we turned it, and we had R total, right? In a DC, you just end up with R total. Okay, then you can do power off of that. You don't have that you do have an R total, but it's strictly resistors. And then we have X of L, which is strictly inductors. We have X of C, which is strictly capacitors. And so we don't end up with this like R total like we did before. We have something else. We call that impedance. What number am I on? 16? Well, I am now. Impedance. 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 An AC circuit. An AC circuit can be described by its components. So if it's purely resistive, meaning it only has resistors, only resistors, it is an R-type circuit. Purely capacitive, and then it's a purely capacitive circuit. If it purely has inductors, then it's an L circuit. But if you start mixing them up, we have like an R, we keep it the same format. We have resistance plus a capacitor. We'd have an RC circuit, or we could have resistance plus inductor plus capacitor. We'd have an RCL is the way we say it, even though I wrote it inductor then capacitor, but RCL. And of course you could have resistance and inductor, which would be an RL. I didn't want to just belabor this point because it was kind of basic. So if you see something that says an RCL circuit, it means it has resistors, capacitors, and coils. So any circuit that is not purely resistive must have this total opposition calculated, and that's where we come up with this impedance. So any circuit that is not purely resistive must have the total opposition to current flow represented as, and that is impedance. It impedes the current flow. And it is represented by the letter Z, or Z if you're from across the pond, as they say. Impedance is not, it is not the sum of each one of these things. So I can't take resistance plus X of L plus X of C and go, well, there's my impedance. Wouldn't it be nice? If that was the case, I would be done right here, right now, and say, there you go. It just add them up, we're done. Test on Friday. But it isn't. Impedance is not the sum of each, but, as my friend Vector says, thank you. Who said that? That was nice. Is a vector sum. And a vector is?
Magnitude and direction.
Well, you got to say it like that.
Magnitude and direction.
Because we are committing. Z is in Z. All right, so it's not a vector sum. Sorry, it's not a sum, it's a vector sum. You got to vector it out. Okay. Now I'm getting down to all these are important points. Okay, because capacitors and inductors have opposite effects. Well, we will use we will use, I didn't put we, but we'll use, when I want to make sure I say it right, use algebra. Don't let that scare you, to find total reactance. Total reactance for a CL, that should be a CL circuit. So first we're going to deal with the C and the L part, and we're going to figure out how that does, and we're going to work off from there. Let's see. This is how we're going to do it. Sometimes it's hard to follow notes. It's easier to talk. But all right. Let me just tell you what's going to happen. Then we'll go back to my notes because that's so much easier. What we're going to do is we're going to diagnose a circuit. And I'm always going to kind of plot it out like this because it just makes sense to me to plot it like this. And so on this axis right here, we're going to have x of L going up and x of C goes down. All right. So if, let's use simple numbers, if I had my x of L equaled, and this isn't a good number, but 5, and x of C equaled 3, then what I'm going to get is my total reactance. Total reactance would be 5 minus 3, which would be 2. Okay, but is it 2 to the x of C or 2 to the x of L? Or I could say, is it positive or negative 2? Okay, it'd be a positive 2. So that'd be 0, 1, 2 on the number line. So my x of L would be right here, a positive 2. With me so far? Okay, so what if x of L was 5 and my x of C was 10? Then I would have negative 5. And so you plot that on the chart, 1, 2, 3, 4, 5. 5 right there. So that's right there. And I kind of work it a little weird because I'm always going to do a line like this. But we'll go back to the first one right here. So, and I'm going to go back through this real slow. I just want you to know where we're going. So that's real easy, right? We've just plotted total reactance. It's just x of L minus x of C. You get a positive number, you go up. You get a negative number, you go down on this little chart right here. Everybody follow so far? Yeah. Okay. Then we're going to plot resistance, which is just going to be on this one right here, this line here. And so let's just say resistance happened to be 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's right here. And so we have 10 out here. And so what ends up happening is we're going to do a vector sum between these two, which is to say that it would kind of look like a square like this. And if we put a point right there, and I made a line come out like that, representing x of L and the resistance, because you always start right here with your x of L, I'm sorry, your Z. This is Z right there. So you start right here, and you see what I did, how I plotted that out? That's kind of important. Everybody see that? Mm-hmm. So I just counted up 5, counted over 10.
Is that, you counted over 10 because of the X?
Because resistance. Okay. I said my R equaled 10 ohms.
Okay.
So I counted over 10, counted up 2, and then I just carried it over out here into the middle of space just because it makes more sense. And then I start at this point right here, always, and I draw this line. And Z then is my impedance. Then you're done, almost. Then you figure out what this angle is right here. This is called angle of theta, and that's your phase angle. So if I had a really nice, perfectly good circuit, like I was balanced out with my inductors and my coils, so I had 5 x of L and 5 x of C. What is my total reactance? 0. So it'd be count out 0, count out, so it's right here. And let's say I had 10 ohms. Well, then my line would look like this blue line right here on that axis, and my angle would be 0. I'd go 0 because that means that they're both in phase, or 360. So okay, we're gonna come back around to that. and I'm going to show you how to do it. And it's really just following the steps. They're not hard. They really aren't. This is almost one of those things where you can almost just work your way through it, get to the end and say, did I do it right? Perfect. And you'll say, thank God. I don't know what that means, but I did it. And I can do it again and again and again, and I really don't know what I'm doing, but you'll pass. So, where did I go? Okay, inductive reactance. Did I say this? I will now. Inductive reactance. Inductive reactance will be positive. Positive because it causes, because B-E-C-A-U-S, because it causes voltage to lead. It causes voltage to lead. And capacitance will be negative. I'm sorry, capacitive reactance really will be negative because it causes voltage to lag. Voltage to lag. What's that? Move it one. I don't understand.
You to do another example of what you did above.
Oh, do another example of the chart? I will.
Okay.
We're going to come back to it though.
That's what I figured.
So, all right. So what does that mean? That means that this x of L, x of C is x total is equal to x of L plus a negative, we'll put that in parentheses, x of C. Or it's another way of looking at it. You could just say x total equals x of L minus x of C. All right, everybody caught up? Make sure you're doing good. Okay. All right. Let's see. Because resistance does not have an effect on phase, it cannot just be added to reactance. We need to figure out a vector sum. Vector is a quantity having both magnitude and direction.
Oh yeah.
There you go. All right. So let's go back to our graph. Do this one more time. So we have our graph. Resistance is on the horizontal. The x-axis, right?
Yes.
Sorry, it's the office. Oh yes, the x. Which
What?
we're my office fans.
Oh,
Trying to think of what.
He was trying to explain to Michael Scott the x-axis. Oh yes, the x-axis. So we have resistance. It's going on the horizontal, so that's my resistance. So resistance will go on the horizontal. Inductance, either capacitive or coils. Geez. What's that? Inductive reactance or capacitive reactance are the words I'm searching for. You sure you guys don't know the signs of a stroke? I might be having one.
You know, I think it's been a long day. Lots of notes.
A long day at the mechanic store. Inductance is on the vertical. Is on the vertical. All right. Wait a minute. Inductance is vertical up. Is vertical, we'll do that. Vertical up. And capacitance is vertical down. Which is to mean x of L goes up X of C goes to the down. You're going to find most things are X of L, meaning they're inductive. The length of the hypotenuse, length of the hypotenuse, Hypotenuse, hypotenuse is Z, which is impedance. So really, that's what we're doing here. We are building a right triangle where we have the X of L leg, or a C. We have a base, and, well, I just kind of drew it backwards, but no, don't draw it backwards. I'll just start confusing people. There we go. A base, and I put that over this way here, so this one just carries over here. So there we go. So we're going to have a leg, and a hypotenuse. And we're just going to work that, and it's not going to be hard. Right? A squared plus B squared equals C squared. So in a series circuit, and we're only going to do series, so we don't actually get into parallel. You're welcome. In a series circuit, Z, impedance, can be solved by, go ahead and say it. Ohm's law. Yes, close.
Pythagorean's theorem.
Yep.
Pythagorean's suggestion.
Oh, you're talking about trig right now.
Yeah. Snuck it in on you, didn't I? Is that really trig? I think that's more geometry. Which is
Trig.
a squared plus
That's yanked it in there. It's
b,
trig.
okay, equals c squared. All right. Now let's just take, but we're not going to use a squared plus b squared equals c squared. We're going to use x total squared plus r squared equals z squared. And can you see where that came from? Let's scroll back just a little bit. So remember, Pythagorean theorem is this thing about a triangle, a right triangle, where this is A, this is B, and this is C right here. So the length of C is A squared plus B squared equals C squared. But we're working with a triangle over here, and I just draw it backwards because it's the way it works, is that we are doing x total squared, and that is the up and down, x total squared, plus r squared, which is down here, the leg. This is r squared, it goes on top there. And, oops, that didn't work out well at all. And then that will allow us to figure out z squared, which is the hypotenuse over here. So that is z squared. So that's all we're doing. So we're going to easily find our resistance, because you guys can find resistance all day long. It's very simple. In a series circuit, R total equals R1 plus R2 plus R3, right? And you can find your X of L because it's 2 pi FL. You can find your X of C because it's X of C equals 2 pi FC, 1 over that. So you can easily find those two things. You can subtract those two numbers and get either a positive going up or a negative going down. So if it was more capacitive, you would just end up with a triangle that looked like this. And that's easy enough, so you can do that. Then you just use this Pythagorean theorem, x squared plus r squared equals z squared, and boom, you're done with almost everything. And then you're practically to the finish line. Now we just have to finish, once we do that, this little angle, which is quite simple. Your calculator practically does it for you, and then a few power calculations, boom, you're done. It's really just that simple. All right, so let's see, we got time for more. Good. So just a few points here. Z, which stands for impedance. Impedance, Z, impedance gives total resistance or opposition. Resistance to current flow in an RCL circuit or LRC or an RL circuit or whatever you're going to put together. The position or angle of the line, that is the line of Z, indicates phase angle. Or the difference between where voltage is and current is. Well, I could write that because it's right in front of me. Phase angle is the angular difference between the voltage and current. It is represented by the Greek letter. It's kind of a zero with a line, which is theta. All right, so now we've got our gang sign, we've got our Greek thing going on, so we could throw that in there, like, yo, theta, I don't know. Yep. I don't know. Am I good to move? Oh, no. Okay. All right, so while you're writing, we'll talk about some. So in a purely resistive circuit, the angle of theta would be how much? Purely resistive. 0. In a purely capacitive circuit, the theta would be, wow, good, 90 degrees down, right? And so in a purely inductive circuit, the angle would be 90 degrees up. Did everybody see that? You know where I get that? Okay, good. I got honest people. I love honest people. So I go back to this chart right here, get a different color, maybe green. So in a purely resistive, how much X of L would I have?
0.
None. There are no inductors. How much X of C would I have?
0.
None. There are no capacitors. But I've got resistance, so this is the only line I would have. So what is my angle? 0. Okay. So in a purely, meaning it has nothing but inductors, how much X of L do I have?
90.
How much X of C do I have?
0.
0. How much resistance do I have?
0.
0. So I only have one line and it goes straight up. So my angle is 90 to the up, and so X of C would be 90 to the down. All right. See, it's not so hard. Yeah.
Will we be still looking at it as if it's a sine wave, or
Yes.
so
Yep.
it would, like period capacitive would be 270, or would it just be 90 going down?
Just 90 going down,
Okay, so that's the first.
because it's 90 degrees out of phase.
Okay, right.
So then we'd say, how far out of phase is the circuit? It's 90 degrees out,
Okay.
just like we talked about. So the voltage just barely begins to go, and the amps would already be peaked. So 90 degrees out. All right, I can move over.
But it's not going towards the negative. It's going.
A capacitive, it goes down. We call it negative.
Okay.
Let's see. So to compute, worry about writing this all out because it makes it more complicated. But we'll do it anyway because we only have a few minutes left. All right. So we did all that to compute phase shift. Okay, to compute So we figured out already how we're going to get Z, and I'm going to work you through a whole bunch of these. We're going to get them. It's all right. We're going to come back around to all this. To compute phase shift, which is the angle of theta, to compute phase shift in a circuit, that is not purely resistive, trigonomic functions are used. Functions are used. And we talked about this back on week 1. Let's see. I want to kind of abbreviate. One of the things I did right here in my notes, and I don't want to do it, is talk about how to find sides. I don't want to do that. So in a right triangle, we know that angle 1 is 90 degrees. So this angle right there is always going to be 90 degrees. That's what a right triangle is called. And given a second angle, the third is easily found. So if I knew this angle right here was 45, then I even know this one over here is 45 because they're all going to equal 180. So the total of all the angles is 180. That's not hard. Sine, cosine, and tangent are functions to solve the ratio of the sides, but we're not going to use that. We're trying to find the angle right here. This is the angle I'm concerned with, right there. That is my important angle. And so we're just going to be able to find that. So we're going to focus in on that rather than trying to solve all these problems with the triangle. So we do have to name the triangle, all right? And so we've got this one here is hypotenuse, HY hypotenuse. Then when I'm referencing this particular angle right here, this one right here, right there, 3 arrows. Hypotenuse is always going to be the hypotenuse. This one side right here, I have adjacent and opposite. This one will be? Adjacent, ADJ, and that means that this one is the opposite. OPP, opposite. Do everybody follow that? Because with this angle, this one is next to it. That means adjacent. And this one's all the way over here, opposite. So that means it's the opposite. So hypotenuse, adjacent, and opposite. And we are going to use sine, cosine, and tangent, which is, I can never remember SOHCAHTOA. I can remember to say it, but I can never spell it worth a dang. I know, but I always have to look at it or I'll screw it up. SOH. So it's not a very good memorization thing for me since that doesn't work for me. SOHCAHTOA, which is to say that we're going to be using either, it's actually arc sine. So sine equals the opposite over hypotenuse. Or we're going to use cosine, which is adjacent over hypotenuse. Or, I'm over here, tangent, which is opposite divided by adjacent. Which is to say that to find this angle right here, and again, we're going to be using the -1, the arc sine, arc tangent, and that is going to help us find this angle. I'm going to walk you through it real careful so that we don't get all messed up here.
Can you
So,
explain real quick why it's -1 or
why it's the arc tangent? Because we're finding angles and not sides. You'd use the sine, cosine, and tangent to find lengths of sides when angles are known. We're doing it the other way. We're finding angles when sides are known.
Okay.
So, wow, it's about that time to go. I know. Well, according to my clock, you have 2 minutes. So, I go by my clock. So, that's a good place to stop. We'll pick this up. Can we fix it? Can we fix it? Can we do this in one more day? Yes, we can.
You can do